All right, so there's lots of views out there on the philosophy of math I think are invalid. You know, they don't answer questions like why is mathematics so practical? Why is it so universal? They can't explain the epistemology. A lot of people in philosophy don't even have a good epistemology. Or they get some ideas like symbolic logic or silliness like that, which don't really help you understand math. Symbolic logic can help in some contexts, it's great, but in general, no. It's more of a specialized thing, not a thing that most people need. But to get some of this right, to really understand it, we need to get a good idea about how the world is, a good metaphysics, a good epistemology. We need to see how we form concepts, how we form generalizations. We need to see the role of similarity, difference, contrast, context in those things. Like when you form the idea of a projectile. That's not just something you like get in contact with, like Plato might think. You get in contact with the idea of the form. Projectile, we get the concept and knowledge of it kind of at once. It's implied in experience. We see in experience, experience is a warrant, a justification, a validation of proper thought. It's the standard of truth, what we perceive. It's our direct contact with reality, the only one we have. So you get to get the idea of projectile. It doesn't just come out of nowhere. It's in a context of things moving, inanimate things. Some things fall, some things roll on the ground or along the surface of water. They're on a surface somehow. Some things are self-propelled, like a bird, like the one that just flew and landed on a tree. And they got some self-propulsion. The effect that some things float down. They're influenced by gravity, like air resistance a lot, so they kind of float. They don't just fall. Then there's some things that we feel the difference. You can feel it dropping. You can feel pushing along the surface. You feel throwing. You see what happens. You look and experience and you see there's this thing that's different than the others, and we see how. It's got this initial force, and then it's going in a local environment, in the small context, where air resistance and stuff like that is insignificant. It goes through the air and falls on the ground in an arc. We see the shape. We see the cause. An initial force and then nothing. An arrow shot, kind of like a bullet shot, a cannonball. In that context, in contrast to other things, we get the concept of it. It's embedded in experience. And there's all these other implied things about it. It's not like a static concept like Plato. It's an awareness of something in the world where there's all these implied properties and characteristics and actions and relationships and generalizations we can get. That's how we form concepts. So, for example, with that, then it's like contextual. Like, for a lot of people, snow, there's not many types of snow, but then some people like to hear about some Eskimos. They have 8 or 18 different concepts for snow. Because they live in it and they need to know and identify for human value purposes and for survival these different types of snow. Whereas a lot of us don't. Snow is snow is snow. So it's contextual and conceptual. It's an identification of things in the world. There's this relationship between the world and how things are and our mind in its nature too. The mind and the world, both of those need to be understood to really grasp what objectivity is. As brought up in the philosophy Pat Corvini follows the objectivist philosophy. Some places, they say everything's in the mind or everything's in the world. There's not as many philosophers who grasp that it's this interaction. Our mind, it has rules, it has a nature, it has, consciousness has a nature, it does certain things. It's got rules we have to follow. That's part of what we have to obey to be objective. And it's not doing whatever the hell we want. It's strict, rigorous obedience to how we know things. So it's objective. It's lawful. And then there's strict causality in the world. Identity and causality are given in the world, and then we identify them. Those are some things that need to be understood. And the fact that we form concepts with similarity and difference. You get a projectile. How are these things similar in measurements versus other things? You know, because we omit measurements of weight, size, you know, as long as it's not too big and not too small, and it's got to be within a certain context, a certain range to actually be a projectile and to be local on the earth and stuff. You know, within that range, we abstract away from the material it's made of, the structure, the weight, the density, the mass, the color. There's all these ranges of more and less, you know, bigger, smaller, heavier, lighter, denser, less dense, more red, less red. You know, like color has a wavelength associated with it. So there's just measurement there. We know about it now that people did a long time ago. So, you know, they didn't know if color was just something like pure quality or if there was some measurement thing to it. And now we know there's a measurement thing to it. So we can understand concepts better than people could a long time ago because we have this basic knowledge that they didn't. And so we abstract away like that. We abstract away from measurements, and that's what we do in math. With math, we're talking about quantity, or like they say, some of the words are multiplicity and magnitude. When you're talking about entities, a whole entity, that's got to be a whole thing to be that. A dog, a dog, a dog, a person, a person, a person, a dollar, a dollar, a dollar. We got multiplicity, repetition of the same kind of thing. And we can see on the conceptual level that it's a unit. In reality, there's these individual things which are similar. That's the fundamental, the metaphysically given. When we conceptualize it the way we think, according to the rules of our mind and consciousness, how we function as humans conceptually, we can make one thing as a unit. And then we see a unit is like an existent from the conceptual perspective. Things are existence. We can see this is one of a kind. It's like a unit of human, a unit of chair. There's this thing here, and there's another one here. They're similar perceptually, but we can see with our conceptual process, it's like a unit. This is one of a kind of thing. Instead of being one thing and one thing that's similar, this is one of a kind of thing. One chair, one human, one lamp. We get that perspective, that unit perspective, and then we can see, as I say, multiplicity. Triangle, triangle, triangle. And then we can start to abstract that eventually and see a pendulum going back and forth. Like 1, 2, 3, 4, a repetition of action, multiplicity. We can eventually conceptualize it like that. Multiplicity of action, multiplicity of motion. You run once, you run against, you run 3 times. I ran 100 yards 3 times. 3 of those things, or structures or whatever. We start out counting specific discrete entities, and then we can get the concept more abstract and start thinking of entities or things or units as actions and situations and structures. Or, you know, we can think of, we don't see a day like we see a chair, but we can get a concept of a day, 2 days, 3 days, a night, or one revolution around the earth, 1 year. We can start to count like that and see situations as like a whole unified thing and start to count them. And then we got, so there's number has to do with measuring multiplicity, and then we can develop the concept of number to get more abstract numbers we got to see how to apply it to like attributes or magnitudes. We're all different heights. We can see. We know one person has a different measurement in that regard than another. And we see people have all these different heights they can be, but it's always within a range. It's never, you never go all the way down to 0 or negative, all the way to infinity. It's got to be within a certain range. And physically it's proven because of scaling and our bones and biology and all this stuff. It's got to be within a certain range of heights. Or you can weigh more or less. It's always within a range. A lamp can be duller or brighter. There's all these measurements there of more or less along a scale. So we got these attributes of things that we can figure out how to apply multiplicity to. You got these magnitudes, these attributes of things, then you learn to get a thing to help you, like one attribute looked at as a thing, a multiplicity to help you measure magnitude or attribute. You get like a foot or a meter, and you see how many meters long something is. 1, 2, 3. Or you step it out initially, like 1 foot, 2 foot, 3 foot. But then you find out, as opposed to with things, attributes always have a little bit left over. You can rarely get exactly like 3 feet or 3 meters in it. So you got to figure out the process of how do we deal with the extra? What do we do? So one thing is to come up with a different unit. Feet versus inches. Yard versus feet versus inches. Mile versus yard versus feet versus inches. Or fractions of an inch. We learn how to divide something into parts and get fractions. And so that's how we start measuring attributes and magnitudes. And that's the basis of math. And then we develop from there measuring all kinds of different things. But notice the basis is in entities, then getting into attributes. So metaphysically, it's attributes and magnitudes and entities and multiplicities, and then we start numbering them, seeing how to measure attributes. And then we develop the process from there, and that's how it develops historically, how it developed historically, how each of us has to develop. That's the root of math and what we should do to prove things. And then when you form things like the concept of 2, again, measurement omission is coming into play. You got this and this. And first you see, oh, that's like this and this. So some people actually say I many. This and this, I many. Because I carry on my eyes. In some cultures that's what I've heard. Or that and that. A dog and a dog. I many dogs. It's a 1-to-1 correspondence. Or hand many. How many people are coming to attack us? Hand many. You got a 1-to-1 correspondence between the people and your fingers. How many dogs are there? Hand many. Or 2 hand many for 10. Then at a higher level of abstraction, people start to see that 3 is 1 more than 2. 4 is 1 more than 3. Number has 1-to-1 correspondence, plus the idea of increasing by 1 to get the next thing. And it becomes a mental thing. Instead of tally marks or pebbles, number is a sound, a symbol we can carry on with us wherever we want. Instead of pebbles in a pouch or something with tally marks on it, we can carry them around with us and then write down the whole number. Much more efficient, saves time, saves space, much more efficient, and practice and thinking and everything, communicating, thinking, so much more helpful. And that's kind of where number comes from. But like I say, I got into that, but similarity and difference. We look at, that's an important concept for getting like 2. As I say, that and that are similar to this and this. there's all these differences, all these measurements we omit, what it's made of, how tall it is, the mass. All these things are recognized as there. We know there has to be some nature, something. But the important thing is that there's this and this. One and one of the same kind of thing. That's how we get the concept of two. By ignoring everything else about it and just saying there's a repetition. One thing and one thing. This, of this, and of this. And then we're going to get our concept of two when we start to put it in a 2, 3, 4, 5, 6. That's the idea. Or for 5, we got context, similarity, difference, contrast. So there's 5 people coming to attack us. We can put it in a one-to-one correspondence. We know somehow, even though these are people and these are fingers, all these differences about them, but the thing they have in common that we can focus on and conceptualize is the one-to-one correspondence between these. The multiplicity is the same. And eventually when you get to a higher level of abstraction, as I say, you see it's called 5. It's 1 more than 4, 1 less than 6. But at first, before you get to that level, you see that there's a one-to-one correspondence just between the multiplicity of the things. It's just their repetition, their act of existing that matters. And that's the thing that makes us so universal across cultures. You don't got to know the nature of the things. You abstract away from that. It doesn't matter if it's chairs, glasses of water, empty glasses, cell phones, whatever. Anything. And even eventually like actions, situations, you can count. There's all these things we know must exist, but can exist in different ways. The context is there in perception. All these things are given, but the thing we focus on is the relationship, the one-to-one relationship of these to these 5 people. These 5 fingers, pretend these are 5 people. That is the basis of our idea of 5. And that's my idea of like where math comes from. So you see about how there's the same process of forming concept here as there is with like projectile. We look at this in contrast to this or this. We see there's difference in measurements, differences in the number of units, the entities, how much repetition there is, how much multiplicity. This versus this. There's obviously a difference. We can see it. It's experiential. When you get to like 50 and 51, you can't see that. You can't experience it. We got to have an abstraction to help us grasp it. Something concrete with the sounds 50 and 51. Then we can like match things up. But try to have someone see and experience 50 versus 51. It's impossible. But we can see a difference between this. So we get this just like in projectiles. We got all things like this, we see are in common. All things like this, we see are in common. This versus this. Then we get this concept of hand many, or this concept of eye many. Just like projectile versus falling object, or object pushed, or feather floating, or something flying. We see in experience this whole rich situation, and we conceptualize it by looking at what's similar to the projectiles and what's different. What do all projectiles have in common? And how are they different from other things in irrelevant respects? Projectiles have weight, other things have weight. These have mass, other things have mass. But what matters in this context is how they're moving. We focus on that. Same thing with number. We look at this versus this. We see in experience that we have it. No Platonic realm needed. Unlike some people, it's not a fiction. So some philosophies of math regard things as like, so there's a Platonic thing. And so people might dismiss the Platonic thing, the Platonic stuff, and say, oh, yeah, math is a necessary truth, but real knowledge is about experience, so math must be a fiction. That's literally a school, major school of thought. Some people think math is a fiction. Some people think it's merely a formalism, even like the great mathematician Hilbert. Wrong. Maybe good at math, but as a philosopher, horrible. The idea it's like formalism or merely symbol manipulation, that's a big school. Or the idea that it's like a social construct, or some of the stuff from Immanuel Kant, where K-A-N-T, German philosopher, where it's silly. So he would think that to try to explain math instead of looking at reality and thinking how things are, but he thought that, the evidence of the senses wasn't valid. You got to get things from pure reason, things like that. So because of his bad premises, trying to force things into what he thought, he tried to like say, okay, you have nothing, that's 1. Nothing in a set with nothing in it, that's 2. Nothing in a set with nothing in it, and a set with nothing in a set with nothing in it, if that makes sense, is 3. And a bunch of nonsense like that, or whatever. And that's kind of where some of this set theory nonsense comes from. But then you're like defining a function as an ordered pair, which is nonsense. That's not what the concept of function is. That strips the meaning out of the concept of function. It doesn't look at similarities, differences, context, as we did with like this and this, where we get 5 and where we get 2. What we need to do is get a good epistemology into play and look at similarity, difference, contrast, context, and see how we form concepts and form generalizations and how we think with a good epistemology like that. Then we're going to really understand math. Because, with a function, you can think also, like, as I said, with projectile, or with where we get 5 or 2. And then when we go through this process of figuring out how to measure magnitudes or attributes of things, how to measure time, electric field strength, things like that, we figure out we need a unit of that kind of thing, and then see how to repeat it. So it's this difficult, complex process we had to go through in history and in our own development to really understand it. It's not like some Dedekind cut or whatever. That's not where we get the idea. That's just like Ptolemaic astronomy. I don't know what the causes are. I don't care. This is just how things appear. Let's put some formalism on things. Just do some math and that's it. I don't know. And then along comes Kepler, thank goodness, doing some research and having a new astronomy based on causes. That's why it was revolutionary. That's why he got it right and others didn't. He wanted to know what was the cause of motion, not just how can we come up with some weird mathematical model to make it up. That's kind of like what set theory is, so far as I'm concerned. It's just something foisted on it. That's not how math really works. That's not how we should prove things. We should prove things by reducing them down to the evidence of the senses, not by doing this set theory stuff. It's awesome. It's beautiful. I like doing some of those proofs in math. I have a degree in math. It's so cool. It's genius. It's amazing how we came up with it. It's amazing what Ptolemy did. Just the genius to come up with that. The epicycles and the equants and moving things around and modifying things to have the calculations kind of work out as close as possible. It's like genius, but it ain't true. It's cool. I love the intellectual rigor, the thought, the effort behind it and everything, but it's not right. There should be something better. Same thing with the philosophy of math. That's what we need. So with the function, we should see what is it that we're talking about? And how is this mental process different than others? So for example, with the function, just briefly, this isn't a full elaboration, but we see how we get some, like, let's say, there's a function between radius and area. It's a simple thing. It's a formula, but it's a function. When the radius changes, the area of something changes. When you can measure the radius, and then you can use that to calculate the area. And there's this relationship. One radius goes with one area. And eventually, you can put that in ordered pairs at a different level of abstraction and all that, but that's not what a function is. It is not ordered pairs. A function is a cognitive processing. It's a cognitive process that relates like one attribute to another. And then what I think you can eventually, people have like abstracted it more, and you can do like a person, like a thing to a thing. And I got to look back in history and stuff, think about this more to see about the development. But that's a basic idea. Maybe, I don't know if it started out, but you can see how like one person has one weight, and at the same time in the same place. You step on the scale a different day, you're going to weigh a different amount, but right then you got one weight, not two. So it's better to think about area and radius at first for something like this to really get the idea, because people can be confusing. Like, what do you mean I weigh that much? I don't. Look, the scale says something different. Then you got to talk about change and becoming and being and staying the same and all this stuff. But a radius, an area, clear. Or you change the radius and height of something, and that changes the volume of a cylinder. So we can have this relationship between one attribute and another. The attribute of radius and the attribute of area. Or attributes of radius and height for a cylinder. And even a cylinder, of course, is an abstraction, but you see how changing some measurements in a range affects this other measurement. Then we get the idea of function from that, where it's got to be one initial gives one ending. If you have a radius of a circle, you can't have two different areas. That's not a function. That's not what we call it. So it's looking at similarities and differences of things like that. That kind of mental process of relating things that gives us the concept of function. It's not, oh, here's an ordered pair, here's a function. Well, what the hell, All kinds of ordered pairs. Like, even if you say it's an ordered pair, but you can only have x and ones, still, that sure the hell not how I, didn't get the concept of function or what it means in the real world. That's more of an abstract thing that comes later. It can help a little bit, but it can be confusing at first too. And that's not the essence of it, We see, like I say, with radius and area, or radius and volume, a cognitive process like that versus some others. This is what gives us rise to the concept of function, and then we can abstract it. That's something we need to do too. See how to get a concept and see where it applies. You got to see, that's why we need to know the range of measurements. What are the range of measurements of something? Like for a person or a projectile. A projectile is something that's only local because it's semi-parabolic. If you go further, the Earth curves. You're not on a flat surface anymore, and you got to consider the curvature of the Earth and stuff like that. And so then it'd be a different context than what we consider for a projectile. Or if it goes fast enough and stuff like that, it'd circle the Earth, and then you'd have like Kepler's laws of planetary orbits instead of like a projectile. So, unless some people might want to consider like the moon a projectile, but it'd be different in my book. But could be some difference in classification there that wouldn't have too much consequence. It'd be more difference of opinion than something fundamentally different. But with function, as I say, we get the concept and then we see what the essence of it is and how it's different than some process where you just relate things. Like Monday can go to rainy, Monday can go to sunny, Monday can go to cloudy, Monday can go to partly rainy, partly Sunday. There's no one-to-one relationship between what happens on Monday with the weather conditions versus radius and area. So this kind of mental process can be contrasted. This kind of relationship between things and quantities. Or we can see if we get some things and we square them, or square root, like sometimes the square root in a certain function can give us on a graph square root of 8, graphing it sideways, 2 or negative 2, or sorry, cube root of 8 I meant, 2 or negative 2. You get two different things. So with that relationship kind of thing versus this, we get the idea of function. And again, we need to see the idea of similarity, these ideas of similarity, difference, contrast, context, and see how measurement omission comes into play. Then we can really get this idea. Then we have a good epistemology to start developing math. As we saw with like getting number, getting function. And that's how we need to see, I think, things in calculus, probability, everything else. It all needs to reduce down to ultimately multiplicity. That's how we first start to quantify, then figure out the problem of how to measure attributes. Then we can, get into more math, but and it's got to be in an epistemology that grasps how we form concepts, how we form abstractions, how we form generalizations and ideas. With this process of similarity, difference, contrast, context, using measurement omission, using the more and the less of things, the ranges of measurements there can be, like more height, more weight, less weight, smarter, not as smart, wiser, not as wise, more acute in observation, less acute. All these things vary in measurement like that. More important, less important. It has to do with values also. You're feeling more angry, less angry, more intense in your thinking, less intense, more focused, less focused. There's just more and the less about most everything, except for quantities, 1, 2, 3. But with attributes and all this stuff, there's always this more and the less that we can quantify with as an attribute or action. So with that, the more and the less stuff, that's how we form concepts and how we abstract. We got to get that down and see how that applies to math, as I say, other mathematical concepts other than like function and number, limit, derivative, integral, all that. Then we're going to have a good developed philosophy of math. That explains when you see what's going on like that. In brief, you see how no wonder math is so universal. Or let's take this. I'll go with that. Okay, no wonder math is so universal, because wherever we can count things, math applies. It doesn't matter what the nature of the things are, the nature of money, the nature of a dollar, the nature of a peso, the nature of a bird, the swing of a pendulum or swing of a swing, revolution, force, the amount of, or like how many chemicals are in something, how much there is, all these different fields have, you don't got to know a particular field. You just got to know about multiplicity, repetition, magnitude. Get that down. And then, you know, there's always multiplicity in those fields. So, chemistry, you got the same thing in different ways happening again. You got actions, situations, attributes. Physics, same thing. You got individual things, you got entities, you can count, you got attributes, you got situations, actions. Economics, you got things, you got attributes, actions. Biology, same thing. Fitness, same thing. Most every single field, there's always things we can talk about, think about, count, attributes of them, actions, situations, and that's what math is about. Not the nature of the things, the causality, but just how many there are, the multiplicity, the magnitude. That's why it's universal, because we're processing that specific aspect. And that's also why it's universal across cultures, because, this is this, no matter what the culture. Doesn't matter the customs, the language, or religious beliefs, the food. Of course, people have developed math to different extents, but this is this, no matter what. And so, universal across cultures, universal across times and places. Magnitude is magnitude, repetition is repetition, multiplicity is multiplicity. No wonder it's so practical, because math is developed from practice. It's about the world in the first place. It's not about some other realm. It's not a fiction. It's not make-believe. It's not a social game. It's our cognitive processing of multiplicity and magnitude, developing that into all the valid math that we have today. And then no wonder also, if you think, this also explains why children can learn it. You don't have to know a lot about the world as such. They don't have to experience or immerse themselves in the realm of physics, or the realm of chemistry, or the realm of biology, or economics, or politics, or philosophy. No. You can have child prodigies in math, because it's about pure magnitude of things. Not pure in the Platonic sense, but just all you have to do is know there's a thing and it repeats. There's attributes and multiplicity and magnitudes, and we can measure them. And then you go off from there. It's much more essentialized and abstract, and takes much less knowledge of, the actual nature of things. What is a dog? Where does it come from? How does it behave? What does it eat? That takes a lot of human experience. That's entirely different. You don't have child prodigies in physics or philosophy, and you never will, because that takes a lot of human experience. That takes immersion in a field. Whereas in math, as I say, it's just repetition, multiplicity, magnitude. And that doesn't take near as much human experience to master. It's kind of there. Easy to see, no matter what. You can just write symbols on a page. 1, 2, 3, 4, 5. There it is. And go. And then, as I say, kind of in the first place, before I start talking about why kids can do it so well, it's practical, because that's how it was developed. Math was developed to understand the world, to grasp things in it, to compare heights, to see how, to better understand and refine how long it takes someone to run a certain distance, how much time it takes to run, or in other words, how much motion. Time is basically, a motion thing. A clock goes around, the hands of a clock go around, or something happens in this cycle over and over, and we use that to time something else. This motion compared to the motion of someone running. The motion of the earth getting back to the same place, and that's 1 year. How many daylight things have we had when the Earth goes around? You got that relationship. You're relating like that. But math relates like attributes, radius and area. And then eventually, like, you can get to ratios of it. You can compare these different ways, like the change in distance to the change in time. And you do that with smaller increments, and you get the derivative. You can get velocity as a derivative of position, as a change, a ratio of changes. Then acceleration is a derivative of that. So no wonder it's practical, because it starts out and it is about knowing reality, knowing about multiplicity and magnitude in specific fields. It's by design. It's about understanding our world. So no wonder it's about understanding our world and it's practical, because that's the whole purpose and function of mathematics. Not to know some other realm, not to engage in some make-believe story, not to engage in some social group, not to be lost in one's head like Immanuel Kant and deal with sets. Math is practical because it is about practical real-world things we need to know to survive. There are this many people coming to attack us. This engine can go this far in this amount of time. That's what it's about. Getting specific measurements from something. So we need to develop that, I think. With that epistemology, then we're going to really get full developed math. I think with what Pat Corvini's done in the objective epistemology, we already got a lot. We got the basis. Then we just need to like fully develop that, and then math will be understood a lot better and will be integrated. That's one thing it needs philosophically. That's one thing I didn't mention at the beginning. It is not integrated with other things. That's an important thing about it. Like with the Platonic idea, that does not integrate with other aspects of knowledge and philosophy and science. With the fiction thing, that majorly does not integrate with other things. But if we get this idea, this shows us how math and logic relate. Math is not logic. The logicism program is failure. Math and logic are different. But this helps us see how math relates to the world, where it comes from, what its foundation is, how it relates to the other sciences, how we think about it, how it relates to logic, how it helps us be rational, how it helps us survive, how it relates to the practicality of reason as a tool of survival. It relates to our biological development and evolution, which is a scientific thing, not philosophic. Some of this, but it's got to integrate to all these different things. Because, look at it this way too, genetics is the way things adapt to the environment. Epigenetics is a shorter term adaptation. It's adaptation more quickly. Consciousness helps you identify more in the moment. It is an even quicker form of adaptation than genetics or epigenetics. When we have a rational form of consciousness, then it makes our conscious adaptation even more powerful. I think that's what it does. And so this idea about math ties in more with that, as opposed to if someone thinks math is a fiction, well then, how the hell does that tie in with the fact that reason is a tool of survival, as you can see, because reasoning is so practical. Science, the practicality of science and the practicality of math are now understood with this epistemology and philosophy. Otherwise, they're not. And then we see that reason is valuable and important. It's an important part of our life. And that's consistent with what we see here about math. And then other things. So there's this philosophic union we can now make with math and other subjects that we couldn't otherwise. So those are some things that show this is correct, this is the right program, that this philosophic idea and epistemology answers all these basic questions and gives us good answers. So this is something I think we really need to develop more, take seriously, and it'll help education more. Math is about repetition, entities in the world. It's about entities and attributes. It's measuring those. And with an epistemology of forming concepts and abstractions by measurement omission. So that's what we need to do to answer the basic questions, make the philosophic connections. We need to have this unity of thought that a philosophy provides. That's one thing. Getting math right is one thing that's kept things from really being unified philosophically as you need to. Science, math, everyday life, and all that. So we need to develop the program of getting the foundations and philosophy of math on an Aristotelian and objectivist metaphysic and an Aristotelian and objectivist epistemology.